Physicists say the universe began in an event known as the Big Bang about 13.7 billion years ago. However, the question arises as to what caused the explosion and why it happened. Over time, we studied and researched the science and history of our universe, and the Big Bang was the main explanation for everything we observed. Countless studies and thousands of scientists were involved in the research, and the collected data always supported the Big Bang theory as the main explanation for the creation of the universe. According to this theory, dark energy is a form of energy that is even more abundant than galactic energy and is believed to be the anti-gravitational force responsible for the constant expansion of the universe. The Big Bang theory was a cornerstone of cosmological research and shaped our understanding of the origin and evolution of the universe. Today's science is significantly different from the past, and with the development of technology, new theories are born. Many times we discover that things we thought were completely true are far from it. Michio Kaku pointed out the official denial of the Big Bang. That's because the James Webb Space Telescope, JWST, discovered 750 new galaxies that don't look as expected. It opens up a new perspective and makes us dig deeper into how JWST is changing our understanding of the universe. Join us on this incredible journey beyond the far reaches of the observable universe to learn more about the large number of new galaxies that have been discovered. These discoveries force us to rethink the foundations of cosmology and the dynamics of the universe. If you are interested in the news about the universe and its environment, please subscribe to our channel, like this video, share it to reach more people, and turn on the notification bell. The images of new galaxies taken by the James Webb Telescope are absolutely stunning. We see hundreds of galaxies together in one image, and the beauty and power of these photos is amazing, something that cannot be ignored. What seems amazing to the common man, however, is just the opposite to scientists. These images are amazing to them, but they don't match what scientists expected based on their theories. In fact, many more galaxies are seen than expected, and these galaxies are different from the others. They are smaller than imagined and really have a significant age. These surprises panic scientists. There is even an article whose title begins with the word panic to indicate the seriousness of the situation. These galaxies are not what they were supposed to be according to established theories. Scientists have long proposed the Big Bang theory as the main explanation for the formation of our vast universe. According to this theory, the universe began about 13.7 billion years ago with some mysterious cosmic event. However, these images cast doubt on the ultimate birth story of the cosmos as previously understood. The discrepancy between theory and observation requires a re-evaluation of long-standing cosmological models and assumptions. Amazing images from the James Webb Telescope have challenged our understanding of the origin of the universe. In particular, these images directly contradict the Big Bang hypothesis, which cosmological theorists have long held as indisputable truth. The galaxies shown in these images appear small, smooth, old, and numerous compared to the predictions of the Big Bang hypothesis. The fact that the observed galaxies are 2 to 3 times smaller than the corresponding galaxies imaged by the Hubble Space Telescope completely defies the expected behavior in an expanding universe. According to the hypothesis, as the universe expands, objects should appear larger as the distance increases. However, these James Webb observations show galaxies that defy that expectation. The smoothness of these galaxies is also completely unexpected. According to the Big Bang theory, there should be irregularities and variations in the structures of galaxies due to the dynamics of their formation and evolution. However, the images show unusually smooth galaxies with levels of complexity and roughness not normally expected for galaxies of their age. This ignores the expected time period for the formation and evolution of galaxies within the framework of the Big Bang theory. These observations require rethinking the mechanisms of galaxy formation and the influence of cosmic forces over billions of years. The beginning of the universe. All the matter, energy, and building blocks of the cosmos were compressed into a highly concentrated point called a singularity. At this point, the density reached an infinitely high value due to the extreme compression of matter and energy. The concept of singularity is based on our current understanding of the laws of physics, especially the equations of general relativity proposed by Albert Einstein. Inside the singularity was all the matter and energy of the universe in an extraordinarily compressed form. This extreme density indicates that under extreme conditions of pressure and density, such as the singularity, enormous amounts of mass and energy were concentrated in an infinitesimally small space. Heat is immeasurable. The temperature inside the singularity would exceed any temperature that is detectable or reproducible in our current understanding of the universe. The energy stored in this hot, dense point was the seed from which the entire present universe began. The singularity marks the beginning of the universe, the beginning of everything in our cosmos. After the initial singularity, the universe began its journey of expansion and inflation. This process took about 13.7 billion years and gave birth to the universe as we know it today. The expansion of the universe began with an extraordinarily rapid explosion known as cosmic inflation. During this phase, the universe expanded at an unimaginable rate, far exceeding the speed of light, as if the fabric of space stretched and stretched, pulling everything into itself. Cosmic inflation played a huge role in the formation of the large-scale structures of the universe. It smoothed out irregularities, homogenized the distribution of matter and energy, and paved the way for the subsequent formation of galaxies, stars, and other cosmic structures. That period of inflation is decisive in explaining the uniformity of the cosmic microwave background radiation. As the universe continued to expand, the rate of expansion gradually slowed. It is important to note that despite rapid cosmic inflation in the early stages, the universe continued to expand at a measurable rate. This continuous expansion is called cosmic expansion, or the expansion of the universe. Scientists have observed the effects of this expansion through various observations, such as the redshift of light from distant galaxies. Redshift indicates that as the universe expands, light waves are stretched and shifted to longer wavelengths, shifting them toward the red end of the spectrum. During this expansion, all the things that make up our universe were compressed into an incredibly small volume. It was clear that matter could not survive in such a compact space, so changes took place. As the universe expanded and cooled, particles such as protons, neutrons, and electrons began to interact with the light and energy around them. These interactions played a key role in the creation of matter in the universe in the first minutes after the Big Bang. This process is called nucleosynthesis, and it is crucial in creating the building blocks of all matter in the universe. One would expect to observe chaotic and disturbed galaxies due to multiple collisions, but the images taken by JWST tell a different story. Instead of chaotic galaxies, the images show well-organized disks and spiral structures similar to galaxies seen in the modern world. This unexpected finding challenges the idea that mergers are a common process in galaxy evolution. If these new galaxies experience little or no merger, it is unlikely that the small galaxies will grow and grow hundreds of times as expected.
This means that these galaxies were never small to begin with. In addition, the optical illusion created by the hypothesis of an expanding universe, where objects appear smaller due to expansion, does not apply in this case either. Therefore, what we have believed until now will be proven wrong. In addition, the age and abundance of galaxies revealed by the James Webb Space Telescope, JWST, also cast doubt on the validity of the Big Bang theory. JWST is equipped with filters that allow imaging in the infrared part of the spectrum, making it easier to study the colors of these galaxies. By analyzing these colors, astronomers can estimate the age of stars and galaxies. These new insights encourage a re-evaluation of the processes that shaped the universe. One of the main mysteries that has fascinated mankind for centuries is the origin and development of the universe. From ancient myths to modern scientific theories, people have constantly tried to understand how everything began and how it evolved over billions of years. Today, our understanding is largely shaped by the Big Bang theory, which states that the universe began as an infinitesimally small dense point and has been expanding ever since. The Big Bang theory emerged from the convergence of theoretical physics, observational astronomy, and cosmological principles. This suggests that about 13.7 billion years ago, All the matter, energy, and time in the universe originated from a single singularity, an infinitesimally small, hot spot. This singularity expanded rapidly, known as cosmic inflation, within the first fraction of a second after its birth. This period of inflation smoothed the irregularities and set the stage for the subsequent formation of galaxies, stars, and other cosmic structures. As the universe expanded and cooled, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, disintegrated and dominated the interactions between particles and matter. This allowed the formation of protons, neutrons, and electrons, which later combined to form hydrogen and helium atoms. These elements were the building blocks from which stars and galaxies later emerged. The study of the early universe and its evolution has been revolutionized by advances in observational technology, such as telescopes and satellites. One of the most important instruments in modern cosmology is the James Webb Space Telescope, JWST. Launched in 2021, JWST promises to provide unprecedented insights into the formation and structure of galaxies, stars, and planetary systems. Unlike its predecessors, such as the Hubble Space Telescope, JWST operates primarily in the infrared spectrum. This feature allows astronomers to look through clouds of cosmic dust and observe the formation of stars and galaxies that are otherwise hidden from view. By studying the light emitted by these celestial bodies, scientists hope to unravel the mysteries surrounding the early stages of cosmic evolution and the conditions that gave birth to the universe as we know it today. JWST's infrared sensitivity also allows astronomers to study the atmospheres of exoplanets, planets that orbit stars outside our solar system. By analyzing the chemical composition and temperature profiles of these distant worlds, scientists try to identify potentially habitable planets and even detect signs of life beyond Earth. This groundbreaking research could fundamentally change our understanding of the prevalence and diversity of life in the universe. In addition to its scientific goals, JWST is a testament to human ingenuity and international cooperation. Developed through a partnership between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, the telescope represents the collaborative effort of thousands of scientists, engineers, and technicians from around the world. Its construction and assembly included cutting-edge technology and innovative solutions to overcome the challenges of operating in harsh space environments. Consisting of 18 hexagonal segments, the total surface area of JWST's primary mirror is significantly larger than that of the Hubble Space Telescope. This increased light-gathering area improves the sensitivity and resolution of the telescope, allowing it to more clearly observe fainter and more distant objects. With advanced instruments and detectors, JWST is poised to transform our understanding of space and answer some of the most profound questions in astrophysics and cosmology. JWST's main scientific goals are to study the formation and evolution of galaxies throughout cosmic history. By observing galaxies from different eras, from the early universe to the present, scientists hope to observe the processes responsible for their growth, structure, and diversity. This includes studying the role of dark matter and dark energy in shaping the large-scale structure of the universe and influencing the motion of galaxies over billions of years. Another important focus of the JWST mission is the study of star formation and stellar evolution. By observing young, newly formed stars and their surrounding protoplanetary disks, astronomers try to understand the conditions in which stars were born and the factors that determine their lifespan and possible fate. This research is crucial to unraveling the complex interplay of gravity, radiation, and magnetic fields that drive the birth and death of stars throughout the cosmos. In addition to studying galaxies and stars, JWST studies the properties and atmospheres of exoplanets orbiting distant stars. By analyzing the light passing through the atmospheres of these planets during transit events, scientists can identify and characterize important molecules such as water vapor, carbon dioxide, and methane. These observations provide insight into the composition, climate, and potential habitability of exoplanets and lay the groundwork for future missions to search for signs of life beyond Earth. The search for habitable exoplanets and extraterrestrial life is one of the most profound questions in astronomy and astrobiology.